Let me get things rolling. We're really happy to have Michael Johnson with us here today. Michael is an astrophysicist at the Smithsonian. He did his PhD at Santa Barbara, but the weather was too nice there for him, and he had to move to Boston, and where he has been ever since at the Harvard-Smithsonian Center for Astrophysics. Michael and I have worked together over many years now. We've had some good hikes in Aspen. We are working together in EHT and on BHEX. Michael is the PI of the BHEX proposal, which I think he's going to talk about today, among other things. But you should know that he also played a key role inside the Event Horizon Telescope collaboration, where he provided a significant amount of leadership in trying times. He has been a spokesperson at press conferences at the National Press Club. He co-led the Imaging Working Group for a while. He was chair of the Collaboration Science Council, and I think you get the idea. He's really done a lot. And today, he's going to tell us about the Black Hole Explorer. So Michael, welcome, and thank you for coming out.
Thank you so much, Charles, for the really kind intro. It's really such a delight to be here to visit you. Before I get into anything serious, can we do a sound check? Can you guys hear me in the back, or shall I adjust this? We're good? Okay. Well, yeah, it's just such a treat to visit here, and part of that is because the telescopes that I work on are all radio interferometers, which have gone from being this kind of niche topic that not many people really understand to right at the forefront of some of the most major astronomical discoveries. And the reason for that is that these are computational telescopes. We record data to bits, and images are formed in computers. And so they have latched on to this explosive growth in computing technology to just really blow the roof off what we thought was possible and enable a series of really exciting astronomical discoveries across many different domains. So I want to tell you a little bit of the story of that, tying it to black holes and the story of the EHT, but it's really a much broader topic. And I do want to tell you a bit more about this, this mission that Charles and I are working on, that's the Black Hole Explorer. So to set the stage, I just love this video that introduces the M87 galaxy. And the wonderful thing about it is that everything you see here is an actual astronomical image. So the M87 galaxy is tucked in between the constellations of Virgo and Leo. It's a giant elliptical galaxy, but it's also about 55 million light years away, which means that even with the best optical telescopes we have, like the Hubble, all you see is this ball of stars with just a hint of a jet extending away from it. We can look deeper into the source using the technique of radio interferometry, then the jet takes over. And as we look at higher and higher frequencies, the jet becomes more and more optically thin, until we get to 230 gigahertz, and this is the first ever picture of a black hole released by the Event Horizon Telescope collaboration in 2019. So I'm guessing most of you have seen this image before. What we think this is hot gas heated to about 10 to 100 billion degrees that's glowing near the black hole. And then the black hole's strong gravity lenses the light that comes near it or captures it when it comes particularly close, carving out this hole in the donut right there. The image is brighter on the bottom than the top. That's a relativistic Doppler shift because the material on the bottom is rotating towards us, and so it's brighter. It's Doppler boosted, and on the top it's rotating away from us and deboosted. And the exciting thing here is that you can basically just lay a ruler on this image and measure how big the black hole is, and it turns out it's about 6.5 billion times the mass of the sun. So it's really a triumph of the theoretical physics to be able to predict that objects like this can exist in nature. And the two scales that are just incredibly difficult to grapple with here are first just how big this black hole is. It's 6.5 billion times the mass of the sun, which is among the biggest black holes in the universe, we think. But also just how small this is on the sky. So the diameter of this is about 40 micro arc seconds. That's about 1,000 times smaller than the diffraction limit of Hubble or JWST. And And radio interferometry is the only technique we know that can make images on these scales. So this is the first ever picture released by the EHT, and then the next primary target for it is actually the supermassive black hole at the center of the Milky Way, Sagittarius A star. Now, Sag A star was actually the crown jewel for the project. It was originally the primary one, and that's because for decades we've been able to study these stars in motion in orbits around the center of the galaxy. And what's kind of amazing here is that these stars, you're seeing them get whipped around on these Keplerian orbits by something that's just not there. It's a complete gap on that image. And so this was the strongest evidence for the existence of supermassive black holes. But the other kind of amazing thing here is that these stars, the gravity is strong enough to pull them into orbits, but the gravity they experience is not very strong. The closest approach of any of these stars is about 1,000 times the Schwarzschild radius to the black hole. And it turns out that the gravitational acceleration experienced by stars at their closest approach is less than what we experience here on Earth. So it's just this gentle tug of a distant, giant source. But the benefit here, though, is it makes a very tight prediction that there should be an object with 4 million times the mass of the sun sitting right there at the heart of the galaxy. And so the EHT looked right in that region. We zoomed in, and we can compare the image that we get to the prediction from the stars. So the stars predict that there should be a black hole that casts a shadow over a very narrow range of radii. And it's the thickness of that blue annulus there. And what's interesting is actually the thickness of that band is not the uncertainty from the stellar orbits. That's actually the uncertainty because we don't know whether or not the black hole is spinning. So even though the stars give us an exquisite measurement of what the black hole's mass is, they can't measure whether or not the black hole is rotating. And that has a pronounced effect on the shadow. So in 2022, we released the first images of Sagittarius A star with the EHT, and it was exactly aligned with this prediction from the stellar orbits. Really, I think one of the amazing triumphs of observational astronomy coupled to this prediction from the theory of general relativity. So just an extraordinary result. So as you can see from this, the game of taking pictures of black holes is very difficult, but it's not difficult because black holes are black. These are some of the brightest objects in the universe. The real difficulty here is that they're incredibly small. And so we use this kind of mysterious technique of radio interferometry to make these images. So before going further, I just wanted to give you a little bit of background on how this works. Yeah, please. Oh, wow,
yeah. So let's say that you have a tidal disruption event during an observation.
Yes.
I know this is integrated, so it's not like a movie, but would you be able to observe emission from the TDE or not?
Yeah, I mean, those are typically on significantly larger scales. The brightest TDEs in the millimeter are 10 to 20 millijanskis, which turns out to be right at the sensitivity limits of upgrades to the EHT. So TDEs are not something we've observed yet. They are something that absolutely will be observed with VLBI at these wavelengths in the next 10 or 15 years. Yeah, so how does radio interferometry work? Well, for that, I wanted to draw some inspiration from ducks. So here's some ducks. They run, they jump into a pond, and they start kicking their feet furiously. And so all of those ducks are, calm on the surface, but underneath, right, they're kicking away, and they're stirring up the water, and it's turbulent, and it's irregular. But the peculiar thing here is that if you look far away, you don't see turbulent, irregular patterns. You see these nice, coherent, outward propagating wavefronts. And if you go out to a pond and see people splashing around or something, this is a totally generic thing. So the toy problem that I want you to imagine is suppose that you go here and you're standing on the boundary of the pond, and your job is to tell me where the ducks are in the pond. But the game is that we'll say that you can't see them, you're blindfolded, and you also can't hear them. So all you can do is you can wade right into the edge of the pond, and you can feel water lapping against your feet. And the question is, can you tell me the distribution of the ducks in the pond just from that lapping pattern against your feet? Okay, so we'll make this into our toy problem, right? So on the left, we have some ducks in a pond that are close together. On the right, they're far apart. We're going to start with the ones on the left where they're close together, and we're going to let them start kicking their feet. So they start splashing the water. It's turbulent and irregular near the center, and on the edges, you see the outward coherent propagating patterns, and you're just imagining you're standing right here. You're feeling that water go up and down against your feet. Okay, so now on the right, we have ducks that are spread out a little bit further. We're going to let them do the same thing, kick their feet, stir it up turbulent and irregular, far away from the ducks. It's nice, coherent, outward propagating motion. So what's interesting here is that there's the most natural thing you could look at is just the amplitude of that sloshing pattern against your feet. And in these two cases, it turns out that's identical. It doesn't tell you where the ducks are. It only tells you how many ducks there are in the pond. But there's a separate thing that you could imagine, and that's suppose that you have a friend standing near you around the pond. You and your friend are both measuring sloshing patterns and can compare them. In the case where the ducks are close together, you and your friend can be very far apart, and you'll see effectively the same pattern. Where in the case where the ducks are spread out, you and your friend have to be pretty close together before you start to see different patterns. So it's this correlation of the sloshing pattern that encodes the distribution of where the ducks are in the pond. So this is kind of a whimsical example, but it turns out to be mathematically equivalent to what we're doing in radio interferometry. So in our case, we're not looking at ducks in a pond, but we are looking at electrons that are gyrating around magnetic fields. And as they gyrate around, they send out ripples of electromagnetic waves. And then we space telescopes far apart, and each of them is just sampling the electric field as a function of time. And the entirety of what we measure is the correlation between the electric field measured by different pairs of telescopes. And that is how interferometry works. And it turns out that it's not some complicated way that this correlation encodes the source. It's a very elegant relationship that's just given by a Fourier transform. And this was first understood by Michelson more than 100 years ago. And so it turns out that every pair of telescopes samples one spatial frequency of the image on the sky, which is like the distribution of the ducks in the pond, is like the distribution of these hot electrons that are sending out these electromagnetic waves. So if the image were a song, each pair of baselines would hear one note of that song. Long baselines hear high notes, short baselines hear low notes, and you want to piece together all of that information, and then you can reconstruct the whole song or the whole image. So the Event Horizon Telescope is not one telescope at all, but it's actually a collection of telescopes around the world that work together using this technique of radio interferometry. What's amazing is that none of these telescopes was created to do radio interferometry. So we added equipment after the fact that lets them work together. So there are two things that you usually have to add. One is you have to add a very precise clock to every telescope so that they can be perfectly synchronized. So it's just like you and your friend around the boundary of the pond. It doesn't do you any good if you're there one day and your friend is there the next day. You have to be comparing your signals at the exact same time. And so we use hydrogen masers to have that very precise time synchronization between the different locations. The second thing that we had to add was high-speed recording equipment. And this is where the supercomputing applications come in. It turns out that doing this experiment requires extremely high sensitivity. And these are continuum sources. So what we do is we swallow huge swaths of bandwidth. So for these images, we were recording data at 32 gigabits per second at every telescope. So we're swallowing as many photons as we can and converting them into bits, and that's how we create a sensitive instrument. And so the EHT required taking petabytes of data in the campaign that made these first images. And all of the planned upgrades to the EHT involve pushing to even higher data rates. That is why we're able to do this now, and 10 years ago it was hopeless. So that is kind of how the EHT works. So that's just this process of creating this telescope, right, of making this image. But the real question is, what do we learn from the image? Where's the physics in it? And for that, the gold standard is the so-called general relativistic magnetohydrodynamic simulations. These are full three-dimensional numerical simulations of magnetized plasma in the curved spacetime near a black hole. These were pioneered by Charles Gamme, and This is one example of the simulations from his group, and these underscore now all of the theoretical interpretation that we do in the Event Horizon Telescope. They've had a profound influence on how we're able to make sense of the observations that we do and connect them to physics. And what's exciting about these is they don't tell us just the image, but they actually capture all of the dynamics of the source as well. So I'll just play this one more time. What's amazing here is that 1 second in this movie corresponds to 1 hour of observations of Sagittarius star, or 2 months for M87. So these black holes, they're very dynamic systems, and we can actually see changes in them in real time. Yeah.
Maybe this is a question I should have asked our Illinois group like years ago, but when you look at these simulations, so I assume this is at like infinite resolution, like really just staring at it. When you want to compare it to observations, I assume you convolve it with some beam, like the beam of the Event Horizon Telescope. So my question is, how do you calculate the beam shape for the Event Horizon Telescope when you have so many different telescopes around the world that you use?
Okay, so like all speakers say, it's my next slide. So this is like my next 30 slides. So you have exactly the right question this is one piece of it, but connecting this to the observation it turns out, fairly nuanced. But let's start with the warm-up. Because the real question is, which of these simulations can we constrain? And I think one of the shocks in the M87 analysis when we were first doing this, and Charles was leading the paper on this, was just how good the simulations were at matching the image we saw in the sky. Right? These are simulations that had been done, agnostic to the observational results, and they were incredibly effective at capturing what we saw. So here's just one example. This is a so-called magnetically arrested disk. It's a simulation with very strong magnetic fields that help shape the accretion flow. The A here is the spin of the black hole. So 0.94 just means it's close to a theoretical limit for how fast black holes can spin. And R high is just a phenomenological parameter that controls the electron heating in the accretion flow. Here's an almost opposite simulation. SANE here stands for standard and normal evolution, but it just means weak magnetic fields in a more turbulent flow. The spin is 0, so this is a non-rotating black hole, and it's that same plasma parameter. And then here's a third guy. This is a weak magnetic field one. The spin has a negative sign, which means it's retrograde. So the black hole is almost maximally rotating one direction, and it's being fed by an accretion flow that's rotating the opposite direction. And we've tweaked that electron heating parameter. And what's amazing here is that when we convolve these with the beam of our instrument, they're all indistinguishable from the image that the EHT produced. So we have these vastly different physical systems, and yet they all would look identical to the Event Horizon Telescope. So this is good news for simulations, that it's able to match what we see on the sky, but it's bad in terms of, it's very hard for us to strongly delineate between these fundamental parameters of the black hole and the accretion properties that we'd really like to study. So we also tried this for Sagittarius A star, and we had kind of the opposite problem. So now, this was a few years later, the simulation libraries have exploded. There's a lot more capabilities now. Every grid cell you see here corresponds to a simulation that takes often weeks to run. As you might guess, red is bad. That means that we have applied some series of constraints based on the data. And we've determined that this simulation is incompatible with some aspect of the data that we see or other constraints that we have from multi-wavelength observations. And there are only 2 simulations here that are actually consistent with all the constraints, but there's one catch, and the catch is that we left one constraint out, and that's how variable the source is as a function of time, right? That's something these simulations can predict. And once we add that constraint as well, all of these are excluded. Yeah.
Yes, I never understood what that meant. So what are these like when you do gravitational wave data analysis, you use Bayesian approach, or when you use WMAP or CMB analysis, you use a Bayesian approach, you vary overall parameters, you look at posterior distribution.
Yeah.
What are you exactly doing in each of these pixels? Like, are you computing a chi-square, or what are you doing?
Is this recorded?
Yes.
I am being recorded.
I think so, right?
Yes. Okay.
Sorry.
Trying to decide what I can say. So I would say our approach to determining the color here is profoundly unsatisfactory. It is a mix, it's typically a mix of a series of constraints based on things that we measure, that we have varying degrees of confidence in, where we're determining binary success criteria. These are not as precise and statistically motivated as we would like.
Yeah, so I knew that already. But
Okay.
like, what exactly is it that makes it red? Give me a
That we should.
Is this being recorded? Oh, shit.
So I think we're talking later. I think each one of them is well motivated. It's not like anything.
Can
I
you
don't
give me
think
like one
anything-
example? Like,
Yeah, one example.
Yeah.
Oh, so one example might be we have observations of these sources at longer wavelengths where we know how large the emission region is. And so we can check with these simulations, we can ray trace them at those longer wavelengths, and we can see, is that consistent? Or another is, do we see an outflow from these simulations? Is that consistent with the measurements of upper limits on outflows from
I
Sag
see.
star?
So you have these other observations, and they have some posterior probability distribution for some observable, and then you compare against the simulations, and you say, is that consistent with that posterior? And if it's like below some like percentage level,
yeah.
then you say, yeah, no, or otherwise yes, and then you color it red or green based on that.
Well, and I would say this is typically then the product of a series of
You
constraints.
multiply them all together. Yeah.
And this is something that, again, I think is well-intentioned. It's just something that obviously we would like to do a lot better and more statistically and formally. Yeah, another
So,
question.
but physically, is it that the simulations have too much structure, or they have, not enough structure? So what is? I don't understand yet. What is the physical part of the constraints that you mentioned?
So an example might be we see a ring on the sky in the EHD images. Do the simulations predict a ring that's that size, or is it too big or too small or too elongated? Or
But the structure is on the size of, like, is it a horizon size or something much smaller? Like, is it because,
Yeah, our beam size is about twice the Schwarzschild radius. So we're not looking at horizon, detailed horizon scale structure. It's kind of
Broad.
bulk properties of the accretion.
Okay.
Yeah, again, I'm happy to talk about this after in more detail with experts, but I think all I really want to convey here is that GRMHD simulations have been an incredible tool for us, and I think we've developed a good sense of what we believe and what we don't from the outputs. But it's also becoming clear that we need better measurements to sharpen our understanding of these systems. And if we want to understand like the most basic properties, like whether or not a black hole is spinning, we have to have better measurements that are guided by GRMHD to tell us what are the exact measurements that would be able to break these degeneracies. And so one way to understand how that's possible is by drawing inspiration from someone else, and that's Charles Darwin. So not Charles Darwin, the naturalist, but his grandson, who was a physicist. So Charles Darwin was interested in this problem of, suppose that you have a star near a black hole. What would that look like to a distant observer? And he knew that there would be some ray from the star that would be bent by the gravity of the black hole, and so you'd see a distorted image of the star. But he also realized that you'd see more than that. So he wrote, each star, in addition to its direct image, will show a series of faint ghosts on both sides of the black hole. There will be a ghost on its left, just outside 3√3m. Furthermore, there will be secondary ghosts on both sides, still closer to 3√3m, which come from rays that have gone a complete circle around the black hole before escaping to the telescope. The successive ghosts of a sequence crowd together more and more closely to such an extent as exactly to counterbalance their increasing feebleness. But then he added, this result seems to have no practical importance at all. That's really in the paper. And what's amazing is that Darwin was right about everything except that last sentence. So why is this important? Well, here's the EHD image. And we think that if we could see with perfect angular resolution, it would look more like this GRMHD simulation. And these GRMHD simulations always have this feature of the photon ring. Now, it turns out the photon ring is not a ring at all. It's actually a stack of increasingly sharp subrings that are indexed by the number of times that light went around the black hole before escaping. So they're filled with physical information because they have self-similarity imprinted on them. To give you a better sense of this, I just wanted to show a quick movie that shows the passage of light near a black hole. So most of the light that comes to us from near a black hole, most of the light in the EHT image, comes from light that's been rather weakly deflected by the black hole before escaping, and that piles up on this sort of diffuse image similar to what the EHT has seen. But black holes are special, just as Darwin noted. If you aim those light rays just right, they'll loop around the black hole before escaping to the observer. They'll make a U-turn. And those light rays that loop around pile up on this thin photon ring feature. And then if you aim the light rays even more sharply, they can go around the front and then the back and then the front again. They can make more and more loops. And each time they loop around, it turns out that as they escape, they will pile up on an exponentially sharper feature. So the full image that we see from a black hole is the sum of all of these different light rays. And that is the reason that GRMHD simulations always show this photon ring, is because it's being introduced from the black hole itself. It's a property of the strong lensing of the black hole. And so if you take a simulated image on the left, so that's an actual three-dimensional numerical simulation, and you draw lines across it and look at the emission profiles, you'll see the structure where it's stacks of increasingly sharp peaks. And that's because these are plucking out for you light that's gone around the black hole different numbers of times. So we started looking into this, Charles and George Wong and I, with a number of others, and got really excited because this was just helping us understand the basic formation of a black hole image. But then the thing that made it even more exciting is the possibility that we can actually go out and measure this. And this comes back to this notion of interferometry. So again, on the left, that's a simulated image of a black hole, and on the right is the interferometric response. So you and your friend are on the pond. The baseline is just how far apart the telescopes are, how far apart you and your friend are, and the y-axis is how correlated the signal is. It starts out at peak correlation when you're right next to each other, and then as you separate, it falls, and then as you go to longer baselines, it'll be structured, and that's what's encoding the source properties. So on that short baselines, the ones that we can see from the Earth, it's a fairly complex response because it's blending all of this diffuse emission structure from the direct image with the photon ring. But what's amazing is that if you go to longer baselines, ones that we could access by going to space, all of that complexity fades away, and you're left with just a very simple damped periodic oscillation. And the reason that that's so simple is that is where you're dominated by the photon ring signal. And the periodicity there is telling you the diameter of the photon ring along the direction of the baseline. Now, one other thing is that there's two curves here, red and blue. That's baselines that are horizontal or vertical. And so they're sampling the structure along two different directions. And what's interesting here is that you'll see that the peaks of the red and the blue are actually drifting with respect to each other. And that's telling you that there's a slightly different diameter in those two directions for that image. It's telling you it's not a perfect circle. And so this is kind of amazing because right, with our eyes, even with the perfect simulated image, we can't perceive that it's not a perfect circle. It seems like just something of academic interest, whereas the interferometer is actually plucking that out for you. And this is exciting because frame dragging of a rotating black hole actually introduces asymmetry in the photon ring. So the asymptotic photon ring of a non-rotating black hole is always a perfect circle, no matter what direction you look. But if you let the black hole start spinning, what happens is the photon ring becomes displaced by the frame dragging, and it also gets compressed in the direction orthogonal to the spin axis. So this is telling us that doing interferometry is a great way to measure the effects of spin on the distortion of the photon ring of a black hole. The interferometer on long baselines is isolating the signal, but it's also giving you the ability to measure its shape, which is where the relativistic effects are encoded. So it's a really exciting opportunity. Yeah.
So just to clarify, when you say displaced, does that mean that the center of the photon ring, if it were some geometric object, is offset from like where the singularity is as like a center?
Yes, roughly. So relative to, say, larger emission that's fixed, you would actually see the photon ring slide. Yeah. So I don't have too much time to get into the details of the photon ring, but I just want to give you a hint of kind of the mathematical elegance of it. So here, this is the three-dimensional space-time of a black hole. The dot there is going to be a photon, and the sphere that you see there is the event horizon of a black hole. Okay, so that's where everything would be trapped once it passes it. And all black holes that aren't rotating have this special distance where if you put this photon at exactly the right distance, it can orbit around the black hole. And it can orbit whichever direction it wants, and you can even rotate that plane because this whole system is symmetric. And the set of orbits forms something that we call the photon sphere. Now, if you start spinning the black hole, then that photon sphere turns into something called a photon shell. And it actually has very similar physics, but it becomes much more complicated. So that guy that's rotating with the black hole has to come almost to the event horizon. It kisses the event horizon. And the guy that's counter-rotating with the black hole has to move out. Now, you can still fire photons over the top of the black hole, but those have to be done at a different radius now. So that orange guy is actually going exactly over the north pole of the black hole, but as it's moving, it's getting dragged around by the frame dragging of the black hole, so it traces out these more complicated orbits, but it still lives on a sphere. And it turns out that at any radius in between those limits, you can fire your photons off, and the orbit that can actually orbit the black hole will live on a spherical surface at a fixed radius in Boyer-Langquist coordinates. So it's this family of spherical orbits that all live near the black hole. Now, why is this related to images? What I want you to imagine is that you just nudge one of those photons, any of them, just a little bit. So if you kick them just a little bit towards the black hole, they will circle inward very fast and be captured. And if you nudge them just a little bit away from the black hole, they will escape to infinity. But where they land on the observer's screen in infinity is really perplexing. And it turns out that where they land, this is the image you would see on the sky. And where they land on that image, the angle depends not on the angle of where the emission is, but actually the radius of where the emitting photons lived. So this is like a holographic mapping where it's actually doing a probe of different depths in the black hole space-time going all the way down, in this case, to the event horizon for those photons on the left. So this was originally studied by Jim Bardeen, John's son, who I guess was here. Yeah.
All your calculations assume that the black holes are at rest, are stationary, right?
Yes.
But what happened if you have matters that fall in or accretion effect that can induce some change to the black hole? I expect the photon ring will also be dynamical, right?
Yeah, absolutely. So in these cases, the accreting material is incredibly tenuous. It's utterly insignificant in terms of affecting the metric relative to the black hole. And so also the light is almost not affected at all from its null geodesics by the properties of the emitting material. The distortion in the angular deflection of the changing index of refraction is like 9 orders of magnitude weaker than the gravitational lensing from the black hole itself. So there are correction factors, but they're negligible. Yeah.
Okay, thank you.
Yeah, so I do love these quotes from Jim, though, who wrote, it's conceptually interesting, if not astrophysically very important, to calculate the precise apparent shape of the black hole. Unfortunately, there seems to be no hope of observing this effect. So again, these theorists just doing this armchair work for fun that are now absolutely at the core of the next generation of black hole experiments. It's really an exciting time. So our hope is to be able to go measure photon rings in nature for the first time. And the real challenge there in extending the Event Horizon Telescope into space to get these longer baselines is the data. So to put this in context, RadioAstron is the most recent mission that did Earth space VLBI, and it operated with a data rate of 128 megabits per second, which is pretty good. The EHT, when it made its images in 2017, we were operating at data rates of 32 gigabits per second, right? And those higher data rates are imperative to get better sensitivity. What we want is to create the Black Hole Explorer, which will require data rates of 64 gigabits per second. So it's just astonishingly high data rates. And the wonderful thing is that this is possible now with existing technology. And that's using this new technique called laser communications. So laser communications have been developed over a series of missions for the last decade or so, starting with this one that was from the moon. But this is just one example that's the closest parallel with what we need, which is called T-Bird. This was launched on a CubeSat. The whole thing, the whole system weighed 2 kilograms. The downlink laser is a 1 watt laser, 1 watt, and it was flying until just a couple months ago. And it's downlinking data at 200 gigabits per second. This is something like 3 orders of magnitude faster than what you can achieve with conventional radio downlinks. So I think this is such an exciting frontier for astronomical research. Right? We haven't even begun to think about what's possible with these types of data rates. Right? There were just a bunch of probe proposals, billion-dollar class proposals to NASA. None of them involved laser comm because it's too high risk. But I think we as a community should be thinking about, what would we do if these missions could do 1,000 times more data? This center is focused on the emerging capabilities of vast data volumes for new ground-based facilities. Right? This will define the next 10 years in astronomy. And that's going to be possible in space as well.
Michael?
Yeah.
That's only for LEO, right?
Yeah, so T-Bird was LEO, right? LLCD is from the moon. Psyche is deep space. These typically they go like 1 over r squared though.
Yeah.
Because they're basically transmitting roughly 1 bit of information per photon. Yeah.
I guess I'll have a question too. So for EHT, as it was done, as I understand it, there were all these telescopes have day jobs, right? And so you're only taking a very, very short duty cycle of data.
Yeah.
That is useful because you have all the instruments observing at the same time, or some subset of them. How does the observing strategy work for Black Hole Explorer? Because of course the satellite itself can observe all the time, but if nobody else is looking.
Well, there's 2 things here. One is that we want to do VLBI more often, right? We know that these sources are evolving over time. We want to study their dynamics near the black hole and injection into jets. We would actually like to be doing VLBI year-round, and that's going to happen on the ground. We were also looking just for fun at what the Black Hole Explorer could do just as a single-dish observatory. So one use case for this is to study oxygen lines that you can't see from the ground. 2 missions have done this, Odin and SWAS. So we did a calculation of, how much more sensitive would BHEX be, even though it's not designed for this. And just because it's using better receivers and better, and a larger dish, it turns out that all of the science you could do in 1 year with those missions, we think we would be able to do in 1 hour with BHEX. So there's other spectral line science, single dish stuff that we can do also as fillers, but we want to do as much black hole monitoring as possible. Yeah. Yeah, so just to lay out kind of the core parameters of the mission, this is one that it'd be a 3.5 meter diameter, which fits within the fairing of a Falcon 9. That's what sets that. Simultaneous dual band observations at something like 100 and 300 gigahertz, sampling 48 gigahertz of bandwidth and orbiting at about a 20,000 kilometer altitude. So this roughly triples the longest baselines of the current EHT. But we can also go to higher frequencies, so the net effect is that we improve the images by a factor of 5 in their resolution. So here's some simulated data. The colored points there are the space baselines, gray are the ground baselines. You get to see that clear ringing of the photon ring. We can turn that into images and compare what we have on just the ground versus what we would get by going to space, where it really locks onto that photon ring structure. And then we can also try to do constraints on the black hole parameters from the photon ring properties, where this would give much tighter constraints on mass, resolving degeneracies that we still have today. And it would also give the first constraints on spin. The other fun thing about this is it's linking to the ground, and so you're actually leveraging the fact that you have these incredibly sensitive ground apertures, because an interferometer doesn't care which telescope switch. All it cares is the geometric mean of the 2 station sensitivities. So it's really by linking with these ground facilities that we can achieve the sensitivity needed in space. The baseline from BHEX to ALMA is the same as linking 2 20-meter telescopes, right? Launching a 20-meter telescope and having it work with a 20-meter telescope on the ground. So I think it's the investment of this billion-dollar class facilities on the ground that's also enabling this type of science. And for those who do interferometry, this is the kind of UV coverage we get. The surprise was that with one telescope in space, we can actually get pretty filled coverage. And that means that we can do conventional imaging as well. So here's just one example of that. This is another simulated GRMHD simulation. Here's what we would get with the current EHD versus what we can get with BHEX. So we're actually able to track these thin tendrils of plasma over time and study really the detailed dynamics. And then all of the sort of deep relativistic constraints that we get come from the time average data, where we're just dumping all of our data into one pot. And that's where we lock onto features like the photon ring. So kind of coming back to the computational aspect, these particular movies, they were made by some grad students and postdocs, beavering away at 2 a.m. A few months ago at a conference. And I guess what I want to emphasize again is that these are computational telescopes, and our images are defined by computational algorithms. The algorithms we need for this telescope haven't been written yet. These are Band-Aid solutions and placeholders. And it's not just that we need better algorithms to deal with these new types of data. It's also that the data volumes are ones that we simply can't manage with our current approaches. So as an example, when we make images today with the current EHT data volumes, we can get away using something like 10 parameter fits, and it takes about 30 minutes of runtime on a laptop. But we want to expand that. One thing we're doing is we're adding additional observing bands. So we want to see these sources in actual color. So we want to do 3 bands observing, and we want to be able to be sensitive to the extended emission in a jet. That roughly increases the parameters by a factor of 300 and the data volume by a factor of 30. Beyond that, we want to be doing these monitoring campaigns. We don't want images, we want movies. This is a simulated movie of what we would be able to reconstruct with a better ground array. That's 9,000 times as many parameters and 900 times the data volume. And then once we go to space and we have much sharper images, it doesn't do much for the data volume. It's just a modest increase, but the number of parameters goes way up because we're making these basically high definition images with many more pixels, many more parameters to fit. So the computational difficulty of this problem is exploding. For the EHT, most of the imaging was done on laptops. We're writing little imaging scripts in Python and that's great. But to enable these major upgrades, we have to change the paradigm for how we're approaching that. And this is true across all of interferometry. Just to give you a sense of this, many of you have probably seen this famous image of HL tau. This was produced, it's one of the first images from ALMA, and I think it was great, right? They released their scripts, it's reproducible, and it's all open source. So that's a big step forward. But coming back to this question of how did you make red, green, and yellow? What are the uncertainties? I think it's almost comical in our current understanding of statistical astronomy that when you look at an image here at these papers, they're publishing a single image. There's no uncertainty quantification. There's no discussion of its sensitivity to either choices made by the user on calibration or any sort of posterior exploration in a formal sense. So in the EHD, when we released our first images, we were very proud of this. We actually had thousands of different images that went into this parameter survey, and we tried to do some preliminary uncertainty quantification. This felt quite novel and, can I say, disruptive at the time. But what's even more exciting is that this is totally obsolete now. It's moved way beyond that. For Sag-A-Star, we actually started this formal posterior exploration process. So it's rather dense grids, and we're actually using a lot of kind of modern software that allows doing these high-dimensional space exploration for complex posteriors. But this is still just the images, and we want to move beyond that. Right now we have this kind of clumsy process where we make images, and then we quantify the images, and then we create these pass-fail tables for a series of different parameters. We make these pie charts, and then we publish constraints. We want to do that in a holistic way so that our data are directly guiding the final inferences on the black hole parameters of interest, like mass and spin. So one thing that I've been really excited about is using simple models to do these types of fitting. And I got started in this business back when we started looking at the EHT data and polarization, where the same image, we can basically lay down the linear polarization structure on top of it because the EHT is a full polarization imager. So we worked with Ramesh Narayan to develop just a very simple toy model of a ring around a black hole that has some magnetic field structure, and trying to map how the space-time affects that polarization structure before it gets to an observer. So this was really just meant as a chance to wrap our head around the problem. We didn't think it was going to be a formal way to interpret the data. But the amazing thing is that this simple little toy model actually did a great job of reproducing exactly the polarized structure that we could see. So kind of motivated by that, there's this whole team of really talented students and postdocs at the CFA who've been developing sort of increasingly sophisticated toy models that capture both the black hole parameters and the accretion parameters. So instead of doing one and then trying to infer the other, you're actually fitting everything in one go. You're able to put in all of these different effects, the synchrotron emissivity, gravitational and Doppler shifts, emission profiles, path lengths through the material, and so forth, and create images that capture all of that and let you fit the data directly with it. So the most recent example is done by a very talented student at the CFA, Dominic Cheng. And on the top, there are those GRMHD simulations, right? This incredible achievement of supercomputing. Down below it is a simple little toy model that has 13 parameters. That's a toy model that captures the physics of the black hole spacetime and also these degeneracies with the accretion flow. And so what we find is that when we can fit these toy models to the data, it's able to infer the black hole properties, but also where the emission is living and start to decouple those. So we've just started the process of trying to map those where we do get formal posteriors on all the parameters we're after. This is the angular gravitational radius of the black hole and spin, the observer's inclination, and so forth. And I think we're just scratching the surface here, right? This is a proof of concept, but it's a really exciting opportunity for more detailed studies. So I'm kind of over time here. Maybe I'll just jump to the end and say, you know, this really is a golden age of astronomy and of black hole science in particular. I'm particularly excited about this mission, the Black Hole Explorer. This is one that we're going to propose as a NASA's Small Explorers mission next year, and it would launch in 2031. And it would take us from these first fuzzy images of black holes to sharp images that reveal the photon ring and let us lock on to light that has actually orbited the black hole before escaping. I think this really leverages the incredible enthusiasm around these first EHT images, but they're able to push it to the next level and get us to detailed, high-precision measurements of black holes. So I don't know, it's such a joy to visit here. I think computational-enabled astronomy really is the future. There are so many opportunities that we're only beginning to explore, and yeah, happy to talk more with you and hear about your ideas as well. Thanks.
Hi, thanks for the very interesting talk. Going back sort of towards the beginning of the talk, is there any information in the higher point correlators between the baseline points instead of just the 2-point correlation between any two radio telescopes? Is there any? I'm imagining we have 4 friends sitting along the edge of a pond.
Yes.
Yeah, is there any information there?
The answer is no, and it turns out that that's a formal statement. We're sampling a Gaussian random field, and it's a theorem that all information about that is contained in the 2-point function.
Okay.
So it's this lovely. I mean, that is not the case in other fields and other measurements, cosmology and so forth. But in our case, we really are sampling basically just Gaussian random noise, and so there should not be any additional information.
Great, thanks.
Yeah.
Yeah, thanks. So how are you selling this to NASA? Like, what's the cost if you do a cost-benefit analysis, right? Like, what's the cost of the mission, and what is like the thing you tell administrators are going to be able to measure? Like, I don't care about the pretty images. I mean, like, what physics do I learn with BHEX that you are particularly really excited about?
Well, so a couple things. One is the cost of the mission is $170 million. It's a SMEX mission. 10 years ago, the NASA administrator sent a note to the community saying, should we even do SMEX missions anymore? Can you do anything with only $170 million? The fact that it's remotely possible to find light that's orbited a black hole for the first time, and I would say make the first direct measurements of a black hole spin at that price point, I think is a bargain. Beyond that, this is just showing a series of other targets that we can observe over the whole sky. Every red source here is another source where the mass to distance ratio is large enough that we'd be able to make EHT type images for a whole population of sources. I'm really only flashing this to convince you that there's some survey science in my talk. So this is our attempt at a survey. We're not going to see millions of sources, but we're going to go from seeing the first 2 images of black holes to seeing dozens of black holes. And we can start to understand their connections to host galaxies with different morphologies and different structures, start to understand how black holes launch jets, how they power them. And so it really is making major strides towards some of the most basic and thorny questions in astronomy that have been central for decades.
So the modeling of this plasma is very complicated, right? These are very complicated systems, the highly anisotropic. There could be many other effects that are normally not necessarily included in ideal GRMHD simulation. So how do you know that, such effects are not going to make a difference to extract the actual properties that you want from the black hole? Because it seems that the main goal is to understand the properties of the rotating black hole rather than understanding the very complicated plasma physics that you have. Because the plasma is more like a tool to understand the black hole. Right.
I would say this is what makes me extremely nervous about these kind of pizza plot constraints, where we have a library of GRMHD, and the terror is that we find some new knob that we're not currently turning, and all of a sudden, all of our inferences about the system melt away, and it turns out we were constraining the wrong thing. So the beauty of something like the photon ring is that it's created by the lensing of a black hole, right? You can work out what its properties are on a napkin, and it should be independent of anything like the EDF of the emitting plasma or detailed properties that we may or may not understand very well. And I think trying to bridge that gap where we have some firm conclusions that can lead us to new discoveries about relativistic plasmas near black holes, without being over-reliant on simulations that may or may not be correct. I mean, that's just always a difficult dance. And we try to be conservative and we try to understand the limits of what we know, but it's just always tough. Yeah. This is a talk. Yeah, Charles does a lot on these topics.
Okay, I think Jeff is next.
Hi. So really interesting talk. Great science. How much does the science output of Black Hole Explorer depend upon decisions made about funding and deployments in ground-based astronomy? Like, are you assuming that you have the current array of instruments on the ground at some duty cycle, or are you assuming we're going to get this great thing because someone's going to go build this other thing in the next 5 years? Yeah, as we've learned with CMBS-4, things like that can change rapidly.
Okay, well that's a particularly tough case, but I would say there's a big cultural difference between NASA and NSF in particular. NSF is aspirational. It's like we're gonna get some funding and do the best we can. NASA does not work that way. We cannot propose a mission to say, well, we think that people are going to upgrade their telescopes. We're going to propose something based on not only hardware that exists next year when we submit the proposal, but hardware that we think will still exist when the mission actually launches. And anything that's even remotely risky, say telescopes on Mauna Kea, or other examples of things where there's a lot of uncertainty, those are perceived as extremely high risk for the mission. So we do have to kind of scale back to just the bare minimum of what we think is possible.
And said differently, are there things that people could be building out there that, if assuming that goes forward, it greatly improves your reach? Like, how does what you're proposing to NASA compare to what you hope you can do?
Well, so one example is we just signed an MOU with NRAO. Okay, this is not actually disclosed yet, but it's a big deal, right? Because if we can get infrastructure like ALMA, where there's national commitments at a multi-decade scale, That's a major foundational secure thing that we can benchmark our expectations against. And so ALMA, for instance, there are major upgrades to it right now, all of which benefit the Black Hole Explorer, even though they're not designed for that, these correlator upgrades and sensitivity upgrades. So any of these ground-based upgrades are things that we leverage, but we have to be very careful about tying our mission success to any of them. Yeah.
So when you showed your map of your anticipated UV coverage, it looked like there was kind of a gap at intermediate baselines. Is that something that you anticipate to be a problem, and could it be remedied by the introduction of additional ground-based telescopes?
So in this particular case, we're actually not showing all of our coverage. We're showing only the high-frequency coverage of BHEX. We also have a low-frequency band, and once you add that, that actually will fill in that missing information to some degree. The ground-based telescopes, the thickness of this annulus is basically the diameter of the Earth. So adding new telescopes on the ground is not going to be what fills that in. But adding more frequencies to the mission would, or, in 50 years, there's going to be fleets of telescopes in space doing an interferometry. We can't do everything we ever want to do with the first mission. In some sense, this has to be a pathfinder, and the way to do really filled coverage, dense filled coverage, probably is going to be later missions that are higher price points.
Thank you for the talk. I might have missed this, but I just want to ask, following Austin's point, I've heard you talked about it yesterday at Astronomy on Tap, but also I've heard Charles talk about this, that EHT wants to work with getting more telescopes on the ground.
Yeah.
So I'm wondering, adding more telescopes, obviously you're filling out the UV space more. How much closer are you going to get towards probing the physics that you want with just ground alone?
Yeah, we think that ground upgrades will go a long way. I mean, that image of M87, it's not only the first image of a black hole, that's the first image the EHT ever made as an instrument, right? It really is the first step in sub-millimeter VLBI imaging. So by adding additional telescopes, we improve the image fidelity enormously, we improve dynamic range, we're able to see things like the jets. There's a lot of work you can do to get at some really rich physics there. We spent a lot of time trying to make sense of whether we could detect the photon ring in particular from the ground. And our conclusion after literally years of study is that there's no way to do that confidently. Right? You have to put on strong priors, which may or may not be true, and there are a lot of ways to get false positives. So the photon ring is the science that really is pushing you to go to space, and if you want to see lots of black holes, you need that angular resolution as well. But I think the future is bright for ground upgrades too. I think that's more tied to jet physics in the nearby sources.
Thank you for your talk. So in the previous question, you mentioned about survey. So my question is, for the team,
Yeah.
is the priority taking the pictures of as many black holes as possible, or focus on one and making a movie to study its dynamics? So what is the priority?
Yeah, so we have our mission baseline review on Monday. So this is where we kind of freeze in the core goals of the mission. And at this point, both studying a population of sources in different classes of galaxies, radio loud, radio quiet, and so forth. Both that and photon ring science are our goals on equal level. That's good and bad. It means if we don't do either, we fail. But it's good that we are trying to preserve that as part of the core mission. And we may have to descope one if cost or schedule becomes jeopardized. Probably we would preserve the photon ring science. But that would just be that'd be an agonizing decision. We haven't had to make it yet. Okay, and I'm also around the rest of the day and happy to chat with people. Yeah.
Hi. Apart from the photon ring, which is a universal feature, what else would you expect to be universal? Let's say you were talking about the movies. Do you expect anything to be universal there?
Do I expect these types of movies to be universal?
Yeah.
I would say there are a lot of features of the movies that you might have expected to have similarly robust properties. We have not found many that hold up, and that's been one of the real insights from GRMHD. So for instance, the rotation speed, this is something, Nick Conroy is somewhere here. So Nick is studying like rotation speed around the black holes and whether that's generic. There's some hints that that's quite promising, but it can also be sensitive to the astrophysics. There are other features in the image that have varying degrees of robustness, but there's usually something you can do to break it. So we have not found something else like the photon ring, I would say, that looks, like it's just peering through all that complexity.
Hi, thanks for the talk. So you mentioned a lot about how measuring the photon ring shape will be able to constrain the spin of the black hole. How will you be able to constrain mass of the black hole relative to like previous measurements via like dynamical channels?
Yeah, so I would say the thing we really measure is the mass to distance ratio. So we usually adopt some assumed distance because we don't make any new measurement there. The photon ring gives you both the mass and the spin. To a crude approximation, the mass sets the size of the photon ring and the spin sets the asymmetry of it. But it turns out to be more complicated than that, and this is a topic of a vast amount of ongoing work. So it's tricky.
On the survey diagram, you had a bunch of quasars with a note about looking at how jet launching might happen. I don't know if that's easy to describe. What you might look for?
Oh yeah, well Charles is leading the JETS program for BHEX, and I'll tell broadly what we want to understand is how magnetic fields in the jets are anchored to the black hole, because that tells you how the jet is actually powered. Right? Conventionally, we've thought that AGN are powered by liberation of gravitational energy as materials falling into the black hole through some mechanism, and now we think that jets might actually be powered by drawing their energy from the black hole, actually slowing down a spinning black hole. This is called the Blandford-Zanayak mechanism. I think it's one of the most extraordinary predictions, and we basically want to understand that interface right at the base of the jet of how are they being launched, how are they being powered, and why are black holes kind of universally creating these objects.
Okay, Michael's here for the rest of the afternoon. Let's thank him again.